Hi, I'm Jim Heffron. These are my lessons in calculus. Today we're going to talk about the chain rule, which is about taking the derivative of a composition of two functions. So let's get started. Now, maybe the composition is a less familiar operation than adding two functions or multiplying, so we start off by thinking about what composition means. If I write down sine of x squared, then I'm taking the sine of the square of x. So I've got two different operations plugged together. It's kind of like addition in that you're taking two different things, but you're taking them in a different way. You're not taking sine of x plus x squared, you're taking the sine of the square of x. Now that operation is called composition and is denoted with a circle. See it there? F circle G. You might read that out loud as F composed with G or as F circle G. The difficulty with F circle G is that the F is written first because we read it left to right, but it's the thing that is performed second. So if I told you that I'm looking at the sine of x squared and I'm going to take x equals 0.7, then you might take the 0.7 and square it. Then apply the sine. That is to say, the thing that you're doing first is the squaring operation. The thing that you're doing second is the sine operation. So although f is written first, when read left to right, it is nonetheless applied second. So words like first and second are more confusing than helpful. Better is to describe f as the outside function and g as the inside function. Okay. You might guess, on the basis of what happened with subtraction and division, that the derivative of a composition is the composition of derivatives, but it's just simply not right. And the first thing you think to try, let's try f of x equals x cubed and g of x equals x squared, doesn't work out. So if you take the x cubed and the x squared, then the composition is the the cube of the square of x. So f of x, of course, is x cubed. That means take the input and cube it. If the input is x squared, then you're taking x squared cubed, and of course you multiply the 2 times the 3 and you get x to the 6th. The derivative of x to the 6th is easy. But if you tried to take the composition of the derivatives, you just simply wouldn't get 6x to the 5th. You just simply wouldn't get it. So f of x is x cubed. The derivative of x cubed is 3 times the input squared. So there I did 3 times the input squared, 3 times the input squared. The input in this case is supposed to be the derivative of g. The derivative of g is 2x. So 3 times 2x quantity squared. When you square 2x, you get 4x squared. 3 times 4x squared. Well, it doesn't matter what it is. The point is it isn't 6x to the 5th. Okay, so the derivative of the composition is not the composition of derivatives. So your first guess is just simply not right. So we've got to figure out what is right. In order to figure out what is right, we're going to look at functions, input and output functions, in a slightly different way than we're used to. So we're used to, since, a long time ago, since middle school, we're used to thinking of the inputs on that axis, on the horizontal axis, and the outputs on the vertical axis, and that's how we picture functions. But in this case, we're going to picture functions in a somewhat different way. We're going to write the two axes, instead of writing them perpendicular, we're going to write them side to side. So here, this will be the input axis, and this will be the output axis. This is the inputs, and this is the outputs. I have two different functions, f of x equals x squared and g of x equals 1 over x. So just to go through them here is x squared, so 0 squared is 0, 1 squared is 1, 2 squared is 4, see the 4 there? And 3 squared is 9. And the point about this picture is that as you move around, for example, when you're at input of 3, the arrows are spreading apart. So there's an action where the outputs are spread apart somehow. Okay, now let's turn and look to the g of x is 1 over x. And here I have, for example, the 9 maps to 1 over 9, which is about 0.11. And 5 maps to 1 over 5, which is about 0.20. And 1 maps to 1 over 1, which is 1. Okay, so we're picturing what the functions do somehow by picturing them in a different way. Instead of writing the axes at right angles, we're writing the axes here side by side. Now, I'm not going to go into it at great length. We're not going to look at hundreds of examples. There's only one point I want to make about about how how you can see what happens with composition here, and that is that interpreting the derivative in this context. And we're just simply going to give the simplest example of what the derivative means here, because I don't want to go into it at great length. It's just a sidelight for us. So consider f of x equals x squared, very simple function. And I want to look at an interval of inputs around 2. I chose 2 just to pick an example. And I'm going to look at 2 plus and minus 0.1, 2 plus and minus 0.01, and 2 plus and minus 0.001. So there's the input interval, 2 plus and minus 0.1, 2 plus and minus 0.01, and 2 plus and minus 0.01. And I just took out my calculator, did it on my computer, whatever the heck, who can remember, and I got the associated output intervals. So 2 plus and minus 0.1, if you square the 1.9, you find yourself at 3.61. If you square the 2.1, you find yourself at 4.41. And again, I'm looking at the very simplest case, just simply trying to give a picture, not trying to explain all the ins and outs of what can happen, just the very simplest case. But the other output intervals, I'm doing pretty much the same thing. And I want to focus on this bottom line because we've seen in calculus you often want to take the limit. And in this case, I'm taking the 001 as the smallest number in my table. So the input output is plus and minus 0.001. Plus and minus 0.001. And let's look over here. So when we look on the output intervals, I think what you see is that it's centered around 4, just like all the output intervals are centered around 4. But it's very close to being, it's approximately equal to, plus and minus 0.004. Of course, we recognize the significance of the 4 is that if you take the derivative of f, you get 2x. And so the derivative of f at 2 is 4. So another way to understand the derivative, besides the ways that we've already given, is that it is the rate at which a small input interval becomes an output interval. Is that in this case, the small input interval multiplies by a factor of 4, becomes 4 times the size. And again, please, I'm not going into all the ins and outs, just simply looking at the very simplest case, because I want to draw this picture. Composition is where you do one function after another. I already talked about how in f circle g, it is the g that's done first, it's the f that's done second. So here in my picture, I'm starting with an a, moving to a g of a, and then finally f of g of a. Imagine in this picture that g expands the input interval by a factor of 4. Okay? And imagine, just imagining that f in this picture expands the input interval by a factor of, I'll make it smaller, so by a factor of 1/2. Okay, that's an expansion. It's a shrink, but a shrink is a kind of expansion. So isn't it clear that together the two of them should have an expansion factor of 4 times 1/2 of 2? That is to say, the expansion factor of the composition should be, you multiply these two together. It's the expansion factor of the left-hand side of this picture multiplied by the expansion factor of the right-hand side of this picture. And the only complication is that when you're on the right side, the start is not a, the start is g of a. So it doesn't say f prime of a, it says f prime of g of a. And I wrote it in both notations. Okay, so that's the chain rule. That's the formula we need. If g and f are differentiable, the composition is differentiable, and the derivative is this. The derivative of the composition is you take the derivative of f and plug in g of x, and then multiply by the derivative of g at x. Okay, so that's the picture from the prior slide written down. I changed from a's to x's just for no especially good reason. Change from a's to x's to move from the prior slide to this slide. And you know how I like to work. I'm going to do a couple of examples. So the first example is the one that we talked about earlier when we said that the derivative of a composition is not the composition of the derivatives. So we know what the derivative of the composition is. We know it's going to be 6x to the 5th. Does the formula tell you that? So here is f prime of g of x and g prime of x. Okay, so I recognize that g prime of x, 2x, that's there. And now what about the f prime of g of x? Well, f is the cube function. The derivative of the cube function is 3 times the input squared. The input in this case is not x, the input is going to be g of x. So I didn't write 3x squared, I wrote 3x squared squared. And then of course x squared squared is x to the 4th, there's one more x to the 4th, one more x, you end up with x to the 5th, the 3 times 2 makes a 6, and so we get the right answer, get the expected answer. Next example, the one that I started off the slides when I'm talking about composition, so sine of x squared, derivative of sine of x squared. So you take the derivative of sine is cosine and the derivative of x squared, but you don't write the key point here, I'm going to say it about 100 times, the derivative of, you take the derivative of the sine, but you plug in g of x. So it does not say cosine of x, it says cosine of g of x, which was x squared. Okay, so the mistake a person can make here, obviously anybody can fill up a minus sign, but the mistake a person can make, and that you will make on the homework, is you'll forget it and write cosine of x. And it's not cosine of x, it's cosine of what was inside. So it's the derivative of the sine part, plug in what's inside, and then take the derivative of what's inside. So very important is trying to make that sort of burn that statement into the slide, is that the chain rule does not say the derivative of the composition is the product of the derivatives. It does not say that the derivative of the composition is the product of the derivatives. You don't take the product of the derivatives. Instead, you have to plug in x squared here, not x. Okay, so very important, and again, you will make that mistake. Everybody does. Unimportant is in the other notation is that it has some advantages, and one advantage you can see that the person can imagine the DGs canceling here. The difficulty here is that if you try to remember the chain rule using this, you will forget to plug in the x squared. So we don't want to do that. So we're going to remember the chain rule in this way. Okay. Second point is for visual clarity as a teaching thing, I often show applications of the chain rule with under brackets. I've been doing it so far, but I'm bringing it up specifically here. So you see the under brackets here and here. And an example, I'm just simply going to take a more complicated case. So suppose you have the square root of 2x squared minus 1. So square root is a outer function, and 2x squared minus 1 is an inner function, and so I'm going to be applying the chain rule. Here's the derivative of the outer function. We know how to take the derivative of square root, and here's the derivative of the inner function. So to help a person organize what parts are parts when there's a lot of x's and y's flying around the page, I sometimes will write under bars. Matter of fact, I pretty much always write under bars. You should not feel obliged to do this. This is a teaching thing. Although I'll say that when I'm doing these problems, I write under bars. So if you don't need it, you're just smarter than that, good for you. You don't need to write it. But I will write it as a teaching thing. And then I went on here, there's a 4 that cancels with the 2 on the bottom kind of stuff. And there's some algebra that cleans up to give this slightly simpler expression. Okay, but the point here is that the underbars are just simply a teaching thing, and for example, the book won't write them, but I find them helpful to organize the parts of the expression when there get to be some complicated algebra. All right, and you know how I like to work. I like to stop when there's something new to work on. I like to stop and do some practice. Now you're going to stop the video, right, and you're going to try it on a fresh piece of paper and see how you do, right? Okay, all right. Okay, so I had the cube of the sine of x, and I took the derivative. The derivative of the cube of the sine of x is you take the derivative of the cube part and plug in sine, and then you take the derivative of the sine. So the derivative of the sine is perfectly familiar. I won't talk about that. The derivative of the cube of the sine of, and plug in the sine, is the derivative of the cube is 3 times the input squared. The input in this case is not x. The input in this case is sine of x. So 3 times the sine of x squared. And you write sine of x squared in this funny way where you put the 2 above the sine. That just keeps it from looking like sine of x squared. Okay, next one. Alrighty, and we recognize that the square root of 5x squared plus 1 is again a composition because we just saw one like it a few minutes ago for no other reason. So here's the derivative of square root. It's 1/2 times times the input to the minus 1/2 power. Minus 1/2 puts it on the bottom of a fraction inside of a square root. And then here's the derivative of the 5x squared plus 1. And again, I cleaned up, there's a 10 that cancels with a 2 here, so I cleaned it up a little bit to get this expression. All right, next one. E to the tan of x. So e to the exponentiating function is the outer function here, and the inner function is tan x. Okay, great. So I took the derivative of the outer function. The derivative of e to the is e to the. It takes a little getting used to, but it's right. And the derivative of tan is secant squared. So outer function's derivative, don't forget to plug in the inner thing, the tan x, not the x, the tan x, and then the derivative of the inner function. Okay, next one. All right, great. So we had the 9th power of tan x plus x. So here is the derivative of the 9th power. It's 9 times input to the 8th power. And the input, of course, is not x. I said it about 100 times already. So maybe I'll give up saying it in a minute. So I wrote tan x plus x to the 8th power. And then the derivative of tan is secant squared plus 1. Right, excuse me, derivative of tan is secant squared, and the derivative of the x is the plus 1. Sorry, misspoke. All right. Secant of x cubed derivative. Okay, so usually by this point a person has a pretty good idea what to do. So you take the derivative of the secant part, that's going to be secant tan, and you take the derivative of the x cubed part, that's going to be 3x squared. So with a secant tan, though, there's a hesitation for just a second where you say to yourself, what do I get? Do I get secant x cubed tan x? What do I get? And the answer is you have to plug in x cubed everywhere where the expression expects an input. So secant tan, it means secant of input times tan of input, and the input is x cubed. Okay, so that's the mistake that a person could possibly make there. So the next thing up is we talked about the chain rule is how to take the derivative of a composition of two functions. What do you do when you have a composition of more than two functions? The chain rule wants us to proceed in steps. You take the derivative of the outermost function, plug in the innermost function, and then take the derivative of what's inside and multiply two together. Now, when the composition is more deeply nested, it's just more the same. It's exactly the same. So here I see sine of square root of x squared plus 1. So that's a 3 deeper. Sine of square root of x squared plus 1. All right, so I'm going to start in. Take the derivative of the sine of. That's cosine of, and then don't forget to write what's inside. Take the derivative of the square root. Derivative of square root. We've seen it a couple times so far, so it should be familiar. 1/2 input to the minus 1/2. And don't forget to put the correct input. And derivative of x squared plus 1. Okay, so it's the same. This right here is the derivative of square root of x squared plus 1. So this, strictly speaking, is the chain rule. It's derivative of the outer times derivative of the inner. It's just that square root of x squared plus 1 is itself requires a chain rule to take. Okay, I don't like to give one example, so I'm going to give a second example, but it says exactly the same thing. Sine of e to the cosine x is another 3 deeper. So we take the derivative of the sine part, derivative of the e to the part, derivative of the cosine of x part. Derivative of sine is cosine, and don't write cosine of x. Derivative of e to the is e to the, don't write e to the x. And derivative of cosine is minus the sine. And again, it shows you why it's called the chain rule, because you kind of chain your way from until you get all the way inside the expression. Okay, more practice, and in particular the first one expects you to remember how to take the derivative of 2 to the, and I think that's fair because we've been doing the homework and been careful to go back and do previous problems from time to time to keep it all fresh in our minds. But if you happen to have forgotten how to take the derivative of e to the, oops, need to erase that. If you happen to have forgotten how to take the derivative of e to the 2 to the x, the formula is 2 to the x times ln2. But you should be practicing that. Okay, anyway, give you a second here to try it. Okay, and here it is, 2 to the ln2, 2 to the ln2. Don't say 2 to the x, say 2 to the sine radical x. Derivative of sine radical x, here's the derivative of sine radical x. I took the derivative of the sine part, and here's the derivative of the radical x. Okay, the other one, the derivative of x times sine of x squared dx. And you see the hint, there's a times there, so in order to take the derivative, the outermost thing you have to take the derivative of is you have to take the derivative of the product of two things, so it calls for the product rule. Okay, great. So I did the product rule, and I happen to be taking the derivative of the first, write down the second, first, derivative of the second. So derivative of x is right there, write down the sine of x squared. There's the x, and here's the derivative of sine of x squared. Derivative of sine of x squared is cosine of x squared times 2x. And I know that you can combine the 2x, you can combine the 2x with the x and get 2x. Fine. But the point is we did the chain rule part. Okay, one more thing I want to talk about. I am often asked in the course, what's with the radians? How come we insist on using radians? Degrees are what I grew up with. People say, I've got a 2x4, I've got to mate with this other 2x4, and they always work in degrees. Nobody ever says my first 2x4 is at an angle of 0.7 radians. So how come I have to learn a different unit? And the answer is that calculus is easy in radians and ridiculous if you're working in degrees. So let's see why. In radians, for example, the derivatives of sine are easy. So the derivative of sine, of course, is cosine. The derivative of cosine is minus the sine. The derivative of minus the sine, well, the derivative of the sine is cosine, and you just carry the minus along. And then you take the derivative of cosine, and that's minus the sine. Minus a minus makes plus, so you end up with a sine, and you end up circling around. So the derivatives of trigonometric functions, such as sine, are comparatively easy using radians. It's all very straightforward. If we try to switch to degrees, though, it becomes a terrible mess. So if you denote the sine function whose input is in degrees as capital S sine of x, and that's common in some contexts, then a capital S function is, we get the capital S function in terms of the lower s function as being sine of x times pi over 180. Right, there's 2 pi and 360 degrees. Canceling the 2 gives you pi over 180. So just as an instance, if I was to ask for the sine of 45 degrees, then I'm converting that to the radians function by taking 45 times pi over 180. The 45 cancels with the 180, and that's sine of pi over 4, and we recognize that pi over 4 is indeed 45 degrees. Likewise, a cosine with a capital C is going to be the cosine with a lowercase c, the familiar cosine, of x times pi over 180. So there's that conversion factor, that fudge factor, in both cases. All right, so let's try taking the derivative of capital S sine. So here's the derivative of capital S sine. We know how to do this now because we have the chain rule. It's the derivative of lowercase s sine of x times pi over 180, and x times pi over 180 is a function of x, so this is the sine of a function of x. So we know what to do. You take the derivative of the sine part, multiply times the derivative of the function of x. Derivative of x times pi over 180 is just pi over 180. So there it is, pi over 180 times capital C cosine, because it's cosine of x times pi over 180. So now I'm going to take the second derivative just to try to illustrate how things are going bad. I got an extra factor of pi over 180. So is that really that annoying? And the answer is yes, it is. Because I'm going to take the second derivative of sine of x. So I'm taking the derivative of pi over 180 times cosine of x times pi over 180. So what do you do there? We know how to take the derivative of a constant times a function, and the answer is you just bring the constant out. Here is the chain rule applied to cosine of pi of x times pi over 180. So it's minus the sign, x times pi over 180, times x times the derivative of x times pi over 180. So there's a pi over 180. So I see 2 pi over 180s. There are 2 pi over 180s. So I end up with minus pi over 180 squared times capital S, the function in degrees, which is what we asked, can't we use the function in degrees? And the answer is, come on, compare the two. Come on. I mean, the first one is perfectly straightforward. The second one is just a disaster. So you don't want to do calculus in degrees. You want to do calculus in radians. Okay, very good. So, a very important. The chain rule is very, very important, and we're of course going to practice it with the homeworks.